Are you ready?
Yeah, I'm ready.
Okay, folks, welcome back. This is our last session. So today we have 3 talks, and the first is by Matej Penciak from Northeastern University, and he will be talking about geometric action angle coordinates for the spin Ruijsenaars-Schneider system.
All right, great. So thanks, Peter, for organizing this, and thanks for giving me the opportunity to give a talk. It's really exciting to, finally get to talk about this kind of stuff in front of like-minded individuals. So as he said, I'm going to talk about some work that's on the archive here, and then a little bit of speculative work that's still sort of very far from being done on a geometric action angle coordinates for the spin RS system. So I'll say a little bit more, or it'll be clear from context what I mean exactly by geometric action angle coordinates. But so the outline for today's talk, I'm actually going to start with the elliptic CM system, or just more generally the CM system, Caligero-Moser. But in the perspective that was offered by David Ben-Zvi and Tom Nevins in the early 2000s, where they kind of do this sort of construction of geometric action angle coordinates for the CM system. And then what I'll do is I'll move on to the RS system in this perspective, state the main result, then go on to maybe a sketch of the proof. And my goal is to end the talk with some dangerous speculation about what all this has to say about things that other people have talked about in this seminar or in this workshop. So in particular, at the very end, hopefully I'll say something about what similar description for the double elliptic system could look like. So that's maybe the dangerous speculation at the end of the talk. So without further ado, I'll get started. And if anyone has any questions along the way, obviously stop me and I'll try to answer them to the best of my knowledge. So what kind of perspective can we take on the Caligero-Moser system, which sort of illuminates the geometry that's going on? So what we'll do is first we'll start with an irreducible cubic curve and pick a base point in its smooth locus. So these irreducible cubic curves is well known. They fall into 3 kinds of categories. So either E itself is smooth, in which case the choice of a base point together with E makes the pair into an elliptic curve. E can also have a nodal singularity, in which case there's a normalization P1 mapping to E with these 2 points Q1, Q2 mapping to the nodal point. And the smooth locus you can identify with P1 minus those 2 points, which is just C star. And so this curve is going to be sort of like our trigonometric version of what's to follow. And then finally, there's the cuspidal singularity, where, I mean, you can think of it as maybe like 2 infinitesimally close points kind of colliding, or really there's this normalization which takes a single point Q to the cusp point, and the smooth locus is just C. And so the perspective proffered by Tom Nevins and David Ben-Zvi is that you can sort of treat all 3 of the Caligero-Moser systems, the elliptic, trigonometric, and rational, all together by just considering some geometry on cubic curves. So to do this, what you do is you start with the Atiyah vector bundle on E. So this is a rank 2 bundle. It's given by the unique non-trivial, unique up to isomorphism non-trivial extension of OE by itself. Maybe a better way of thinking about this that'll be relevant a little bit later is you can think of this as really the tangent sheaf on E as well. So A is somehow kind of like a modification on just the differential operators of order less than or equal to 1. And then we form this surface, this ruled surface E natural, which is just the projective bundle associated to this rank 2 vector bundle A. And the section at infinity is coming from this projection down from A into the tangent sheaf. So what does this geometry look like? There's one perspective that's already kind of appeared like very, very long ago by Tribush-Verdier on tangential covers. And so what you can do is you can just take the compactification of the cotangent bundle, which is just going to be a trivial P1 bundle over E, and do a sequence of blow-ups and blow-downs. And so what we'll do is we'll take a point B naught along the zero section of this trivial P1 bundle and blow up to get some exceptional divisor ZB naught. And then we'll choose a P1 inside of the linear system E infinity plus ZB naught and blow it down. And the resulting surface turns out to be equivalent to our surface E natural. And from this construction, you can see that the E natural doesn't have a section at 0 because we've sort of contracted it down to a point, and it really only has the section at infinity. This is another way of seeing that is just that the short exact sequence on the previous slide doesn't split, and so there's no section at 0 as well. But then this Stein surface, which is the open part taking away E infinity, as I said, already appeared in the work on elliptic solitons back in the 80s. And so this geometry has been familiar for a while, and it was, it wasn't surprising that this would appear in the context of the Caligari-Moser system. Okay, and so this is kind of the main definition, which gets us to the Caligari-Moser system. So what we do is we fix a torsion sheaf supported along the section at infinity. And what we'll do is we'll define so-called T-framed CM spectral sheaves. And so what are these guys? These are pure one-dimensional sheaves. So they're sheaves which have pure one-dimensional support on E natural. And they're framed so that there's an isomorphism, a fixed isomorphism of the framed spectral sheaf, or of the spectral sheaf restricted to the section at infinity with the specific torsion sheaf that we've chosen. And so then these are, at this point, we could call it a day and talk about the moduli stack of these kinds of things. But in order to get a well-behaved moduli space, we have to add in some additional cohomological constraints and some additional stability constraints. And so these can be thought of more of as something like technical conditions in order to get the ball rolling on these kinds of things. But the basic idea you should have in your head is that these are in almost just like pairs of a curve together with a line bundle. So what we're doing is we're kind of jumping directly to the action angle coordinates for the CM system.
What's the number of particles here? Is it the 2 particle?
So at this point, I haven't said exactly how many particles. This comes into the theorem. So what you do is you define this moduli space here of frame spectral sheaves where the push forward down to the base curve E is going to be
that's the definition of the CM spectral sheaf, and then the CM space comes next, right? So, okay.
Yeah. So CM spectral sheaves could in principle have any number of particles, and the number of particles comes from the rank of the vector bundle you get when you push down.
CMN, it will be like a stack, like in Etinhoff treatment, for example, right?
Yeah. It'll be, and it'll be disconnected depending, and it'll have some connected locus depending on the number of particles. That's right. But then, as I've done here, I've scrolled down and you see that the main theorem that David Ben-Zvi and Tom Nevins had is that you can identify this space as this moduli space of CM spectral sheaves framed at infinity by this particular type of framing with a completion of the K spin and N particle CM phase space. And furthermore, there's a natural set of flows that you can put on this space of sheaves that they call tweaking flows, and I'll continue their terminology, call them tweaking flows. And the CM flows turn out naturally to be identified with these tweaking flows under this identification. And so what I'll do next is I'll tell you exactly what these tweaking flows are.
Sorry, may I just the question?
Yeah.
I'm trying. You're talking about
it could be rational, trigonometric, or elliptic. So if E is the nodal curve, it'll be trigonometric. And if E is the rational curve, or is the cuspidal curve, you'd be talking about the rational.
So is there like any relation to like Lax pairs, like when you're talking about action variables, or Lax pairs supposed to be some section or something, right?
Yeah. So I'll get to that. Yeah, you'll see where the Lax matrix comes in. So actually, it's interesting in this perspective, the M in the Lax pair doesn't show up necessarily, but the Lax matrix itself does, the L.
Yeah, M is related to Hamiltonians. It's more related to which time you pick, or it's normal.
All right. So first, before oh, sorry.
Could you explain the framing for the spinless case? K is 0.
Oh, K is 1 for the spinless case. So you have to always have a framing, and for K equals 1, it's the spinless case. Great. So so let me now explain the tweaking flows. And so what you do is you take the spectral curve, the support of your CM spectral sheaf, and you pick the point at which it intersects in E infinity. So in the previous case where I was talking about the spin flows, we were just taking P to be the base point, but in principle, the divisor of intersection can be as wild as you want. I mean, I guess subject to some geometry about the world surface. And these flows are actually just really natural flows that you see in the context of this work by Bailenson and Drinfeld on the affine Grassmannian, et cetera. So what you do is you take D, the formal disk at the point P of intersection. So this is a formal disk living inside of your spectral curve, and you'll consider the spectral sheaf restricted to the complement of the point together with the restriction to the formal disk, and the transition map along the punctured disk is given by some function phi, which is going to be in general some Laurent series. And what you'll do is you'll just modify phi by a particular choice of Laurent series. And then this defines a tangent vector at the point F inside this moduli space. And the key observation that Tom and David had was that if you consider the particular cases of z to the power k, where here k is bigger than or equal to 0, the flows coming from these particular elementary modifications of the sheaf are exactly identified with the kth time flow for the CM system. So this is how the tweaking works. You're kind of just tweaking the sheaf at the point, at the framing point. And so it's important that you tweak the sheaf at the framing point because you want to consider the flows that are tangent to framed spectral sheaves. So you don't want the framing to change. So you really need to look at tweakings along the points at infinity. Okay, and so then going back to the other question about how can we see the Lax matrix coming from this kind of story. So I like to think of this as like a really compelling calculation. This isn't by no means a proof of the theorem of Tom and David. There's a lot of steps that go into it, but one of the key observations is that there's an open locus inside of here where the push forward vector bundle actually decomposes into a direct sum of line bundles. And so the push forward, one of the technical conditions is that W is going to be a degree 0 vector bundle on E, and a generic, for at least for E smooth or in the smooth locus, generically rank 0 vector or degree 0 vector bundles decompose into direct sum of line bundles. And if we work out and now you sort of play the usual game that you do, for example, in the Hitchin system, where you can relate Hitchin spectral curves to to like Higgs bundles, etc., what you can do is you can see that the action of the structure sheaf on F inside of E natural will descend to a meromorphic Higgs field on the base. And then if you just work out what the ijth component is, it's exactly a section of, well, it's a map from this to this, or exactly a section here of this particular line bundle. And at least in the rational case, what are you looking for? You're looking at you're looking for a function which has a pole at 0 and a 0 at the point qj minus qi, which you can very easily just write down in the rational case as 1 over z minus qj minus qi, or more generally written in terms of elliptic functions, it's this. And what you get is you get the usual CM lax matrix that's been written down with spectral parameter. And so this is where the lax matrix comes in. So I guess what I should say here is that this is for I not equal to j, and for I equal to j, you're looking at H naught of O of B, which is just C, and you're given just the choice of a constant. So these are the momenta along the diagonal. And so this is how you recover the lax matrix. So hopefully that answered your question.
Yeah. This is ratio is the same as Andrei Zoto was talking about.
Yeah,
yesterday.
exactly.
It arises.
It's the
and you've chosen your B to be 0.
Yeah. So I guess you can sort of do I guess a linear change of coordinates so that the base point you can identify with 0 inside the vector space.
Yeah, I'm
so
trying to understand your choice. That makes sense.
Yeah. Great. Any other questions? Okay, great. So this compelling calculation should at least give you some hope that I'm not lying to you. The proof that you can go through these steps is kind of the main idea. And so now let's go to the Ruijsenaars-Schneider system. And here the description is going to depend on an extra parameter. So what I'll do is I'll pick some alpha inside the compactified Jacobian of E. If E is smooth, this is just identified with E. Well, I guess the point is that if E is not smooth, this is also identified with E. So it's important that you choose the compactified Jacobian. And then this point alpha is going to correspond to a line bundle L alpha, or more generally a rank 1 torsion free sheaf. And what you'll do is you'll consider this projective ruled surface S alpha bar, which is just the projectivization of L alpha plus direct sum of OE. And compared to the previous picture, now this surface actually does have 2 projections, which would correspond to the 2 sections E0 and E infinity. And so this is kind of like a pictorial diagram I have for what the surface S alpha bar looks like. So it's going to be some surface with 2 sections E0 and E infinity. And as before, we'll define the space of RS spectral sheaves to be some pure one-dimensional sheaves on S alpha bar. And what I'll do is I'll fix a torsion sheaf that's supported along E infinity union E0, here in green in this picture. And the framing of this RS spectral sheaf will be an isomorphism of F restricted to the intersection with this fixed torsion sheaf. And then,
are all these surfaces holomorphic symplectic, or is there a divisor that you need to be careful about?
They're not symplectic, they're Poisson. And that's, I think I say a word about that on the next slide, but they are Poisson surfaces. They're birational to, or I guess an open locus of this guy, Right.
There's a divisor in there where, yeah, okay.
Yeah. So this kind of looks like E C star, or there's an open locus inside of here, which is E cross C star, and you can define just like DZ wedge DW over W as your Poisson structure. And so there's this divisor where W blows up at infinity and at 0, which is going to give you the degeneration of the Poisson structure.
Great.
And so there's kind of this open locus inside of here maybe I could call it S alpha 0, which is going to be the symplectic part, but then there's the parts at infinity and parts at E0 where it blows up. Right. Let's see. Right, and as I was saying, there's these stability and cohomological conditions that you have to place on these in order to get a well-defined moduli space later. And so that moduli space here is going to be denoted by RS and alpha, n being the number of particles and alpha being this extra fixed parameter that you need in the RS system. And so I'll say a word about what the role alpha plays later when I compare this to the CM system, but for now it's just some extra parameter that exists. Okay, any other questions?
So to get the CM system, you need to send it to take a limit or something? Yeah.
So we'll see what limit to take later. Okay, so turns out that most, if I just pick some random torsion sheaf T, most of these spaces are going to be empty. In fact, the geometry of S alpha implies that if sigma is the support of F, then it has to intersect at D at E0 and at E infinity in a very particular way. And I use this relation is very commonly used in the arguments. So I make it a relation star here. So the divisor at infinity is a shift of the divisor of 0. Where I'm using the group action here. This is the sum as a group action inside the elliptic curve.
And 0 and infinity there are where your symplectic, the 2 points that you had previously, is it? And so this is something about how your curve is intersecting with those.
Yeah. So this is the picture over here. There's the 2 points here. I'm pictorially identifying as a point, but in general, it could be a divisor. This curve can come back down and it could intersect like many different points if you want. And D0 and D infinity have to be related by a shift, which is the N sigma minus B, or alpha, sorry, N alpha minus B.
Thank you.
Yeah. Oh, sorry. Yeah, it was, this is supposed to be an alpha here. Okay. Right. And like I was saying before, there's some open locus inside this moduli space, which consists of pairs of a spectral curve together with a line bundle, as the usual kind of picture of a spectral curve and a spectral line bundle, but there are more general spectral sheaves. And so a lot of crazy things can happen. So for example, you can have non-reduced curves. You can have singular curves, curves which are smooth, but even the spectral sheaf along the curve is maybe a higher rank vector bundle or some other type of surface or type of sheaf. And so the spectral sheaves can be a lot more general than just the pair of a curve together with a line bundle, which is giving you the fact that this is, more of like it's a completion of the phase space. And then going back to the question, another way of seeing this space is RS and alpha. It inherits a Poisson structure as a moduli space of sheaves on the Poisson surface. And so I describe what the Poisson structure on this surface is, and there's a general machinery that says that if you have a moduli space of sheaves on a Poisson surface, it inherits a structure of a Poisson variety. And the framing of the spectral sheaf at infinity and at 0 actually takes a symplectic leaf inside of the full moduli space of sheaves. And so this thing turns out to be a symplectic manifold, or sorry, a symplectic variety, and it's given as a symplectic leaf in some larger Poisson variety of the moduli space of sheaves. Okay.
At this stage, there's been no mention of action angle variables. Is that right? So there's no mention of pairing of moduli of your curve with anything.
That's right. So this is kind of where the geometric action angle variables come in. So the curves have to live in a particular, so the curves, if you want pi push forward of f to be a rank n, the curves have to live in a particular linear series inside of your surface. It'll be something like NE0 plus the fiber over the base point or something like that. And the action angle coordinates are essentially, you know, these are going to be your angle or your action coordinates, the coordinates on the linear series that the curve lives in, and the angle coordinates will be the choice of spectral sheaf on that curve.
And what guarantees that you've got the same number of each?
I mean, you can calculate the dimension. So the dimension of this is n, and then I guess there's an argument. Well, I guess, yeah, you know that the dimension of this is n, and you know the dimension of the space is 2n. So I guess it kind of works out. But there is, I guess, some work that it's not obvious, but there is some work that you have to do to guarantee that they have the same dimension.
Right. Yeah, right. Normally, I would have to use properties of the symplectic form of the space it's sitting in to get a pairing. So I mean, is that implicit in this more general picture that you were telling us about?
Well, you can identify what the symplectic form on this space is in terms of, so eventually I'm going to identify this space with a space of Higgs fields like I did for the CM system. And you can identify what the symplectic form is in terms of like traces of the Higgs fields and stuff. So it's a pairing that exists on the Higgs fields. And that's kind of where you get the pairing between the action and angle coordinates. So I don't know if that answered your question.
Yes, it did.
Okay, great. Okay. So now if we restrict to the case where our torsion sheaf is similar to the spin torsion sheaf that we had for the Caligari-Moser system, but in this case, it has to be supported at both P0 and P infinity, then what we do is we call our resulting space this RS, K, N, alpha, etc. E. And then finally, we can define a collection of flows on this space as we had before, called the tweaking flows. In this case, we actually have sort of two opportunities to tweak the sheaves at either at P0 and P infinity. But it turns out that they both define the same Lagrangian subspace inside of the tangent space. And so there's going to be some relation. I mean, I guess abstractly, you know, they define the same Lagrangian subspace. It's not 100% clear like what the formulas are that relates the two, but it'll be something like, you know, if I use an F over here, it would be something like using a 1 over F over here. But this is that it's you know that they define the same Lagrangian subspace more abstractly just by looking at dimensions. And so now we have our space, we have our tweaking flows, and so there's no surprise that the main result is that the space RS, K, and alpha of E can be identified with a completion of the K-spin n-particle RS phase space. And the RS flows come from the tweaking flows of the RS spectral sheaf. And so then, as opposed to the Caligari-Moser setting, I'll actually give you a sketch of what the proof looks like. So does anyone have any questions so far, or are you guys ready to see the proof? Okay, great. So the proof is I like to think of the proof as being sort of split up into 3 different parts. So the first part is this identification with the Hitchin system. And so if we take W to be the push forward of our spectral sheaf, then just play the usual game that you do with the Hitchin system. So we look at the 2 Stein surfaces S alpha minus the section at infinity and S alpha minus the section at at 0. We end up getting 2 separate Higgs fields, eta 0 and eta infinity. And they're meromorphic and they're L twisted Higgs fields. So then you use some various properties about the geometry of the surface S alpha to conclude that these two Higgs fields are in fact actually invertible away from the points P0 and P infinity. And then furthermore, the relation star that we had between the points P0 and P infinity actually implies that eta 0 is the inverse of eta infinity, but shifted by this factor n alpha minus beta. And so then we're sort of so it was this it was this observation here when I finally figured this out, is when I realized I was kind of on the right track. Because what you can do is you can then identify the composition from W to W twisted by P0 plus and P infinity, which could identify this space with the space of multiplicative Higgs bundles with values in this sheaf right here. And so the abstract Higgs bundles with values in a particular sheaf was worked out in some work by Dennis Gatescory and Ron Donaghy. And in this case, we end up getting some sort of space of multiplicative Higgs bundles. So now that we can kind of identify the space as a kind of like a multiplicative Hitchin system, what we do now is we repeat this compelling calculation we had before in the CM system. So what we'll do is we'll restrict to an open locus inside of this phase space where our push forward vector bundle can decompose into direct sum of line bundles. And in coordinates with respect to this decomposition, eta 0 and eta infinity essentially become elliptic Cauchy matrices. And so what you can do is now you can just do a little bit of calculations with elliptic functions, and you'll see that the composition, or written in terms of just eta 0, like this, ends up recovering the RS lax matrix. And so I make a note down here actually that this RS lax matrix that you get is in fact this factorized RS lax matrix that we've seen before that was mentioned in Andrei Zotov's talk yesterday, or maybe 2 days ago. No, it was yesterday. In his notation, he called it G of Z. So in our case, this eta 0 of Z is this G of Z, this intertwiner in the IRF vertex correspondence. And so we get a very particular form for the lax matrix when we work it out in this geometric perspective.
So in the CM limit, one of those factors becomes trivial or something, or is it because
in the CM limit you end up getting this gauged factorized or gauged CM lax matrix. So I think in Andrei's,
you said geometrically the origins eta 0 and eta infinity because they come from E0 and E infinity, right? And then you blow down one of them on the CM limit.
Yeah, and in the CM limit, this H bar goes to 0. So this composition, eta 0 and eta infinity really are inverses of each other. So there's no extra data there.
Yeah. Okay.
Yeah, I guess I used H bar here. This H bar is again this alpha, this quantity alpha minus b, or sorry, n alpha minus b. Okay, and then finally, once we see that we get the lax matrix, we want to define the flows on this space and make sure that the flows are actually coming from this particular, the appropriate Hamiltonians associated to the lax matrix. So you define the Hitchin system, which is going to be a map down to some Hitchin base inside of this big direct sum of twists of a line bundle, together with in coordinates is just the traces of powers of the lax matrix. And then the final step is you show that the tweaking flows on F end up being matched up with the Hitchin flows on the vector bundle together with the two Higgs fields on it. And this is how you can identify the lax matrix as really being the generating function for the Hamiltonians of the various flows on this space. And so this is kind of like the sketch, very cartoon sketch of what the proof looks like.
Matej, did you tell us that you could have all of these really strange sheaves? So I wouldn't be expecting to get the standard lax. I mean, I don't understand in what these very strange objects are, but they're in principle in what you've told us. So, I mean, are they appearing in this lax, or does this lax tell me about these strange objects that I don't normally think about?
Well, no, because the lax matrix is really only appearing on this particular open locus. So you can only really calculate the lax matrix in coordinates on this particular open locus inside of the space, which is where the sheaf decomposes into a big direct sum of line bundles. Outside of there's, I guess maybe you could probably do some work to figure out what this composition looks like and actually figure out maybe in coordinates what it would work out, but I don't know exactly what that would exactly look like. And so it's really outside of that locus where the sheaf can decompose into a direct sum of line bundles. I'm not sure the original formula for the lax matrix could say very much.
Okay, does this have any physical picture as to what's happening as perhaps the particles are heading off to infinity, or?
It's closer, I think, to what's happening when the particles are approaching, colliding.
Colliding.
And yeah. As the particles move off to infinity, I think what ends up happening is your spectral curves become well separated, and you can approximate them as being somehow like just sort of flat sections over the disconnected flat sections. But as the particles are coming close together, this is where like crazy things like singularities and non-reduced curves can show up.
Got you. Thanks.
Great. Any other questions? Sort of going through these slides a lot faster than I thought I would, so I'm open to more questions. Okay, so what kind of going back to this question from, I think it was Peter or someone asked this question from a long time ago, what is the role of alpha, or sort of what limit would I take for alpha? So I guess here I said 0, but I should be more careful. This is this alpha to b limit. So if I take alpha approaching b, there's a particular limit I can take where this L alpha direct sum OE, instead of approaching OE direct sum OE, what I'm going to do is I'm going to take a particular limit where this direct sum approaches A, and this limit is going to limit my surface S alpha in the case of RS spectral sheaves to this surface E natural, which I had in the CM case. And then you just have to match up the cohomological conditions and the various framing conditions that exist on either side. And you see that in this limit, RS spectral sheaves will limit to CM spectral sheaves. So I guess in the context of like Seiberg-Witten theory, this thing could look like the, R to infinity limit, or maybe the R to 0 limit. I'm not a physicist, so I don't really know exactly which one, but this compactification down from 5D to 4D, you can take the limit, I guess, as R goes to 0, and you'll get the 4D theory. And so this is sort of like the RS to CM limit in that case. Or the way I understand it is alpha is kind of like C inverse, and you're taking this relativistic RS system to a classical limit.
I still don't see how the irrational appears. If you just basically the alpha minus b is that shift, right? That you had on the other component on E infinity, but
yeah.
So, but then you said, I'm just looking at the previous slide. You blow down E0 to get the CM sheaf, right? It's you do need to do some other action, right? So it's not just send alpha to B, or is that, you think that's enough?
No, what you do is you send alpha to B, and I mean this, yeah. So I guess to be more precise, what you can do is you can define this big surface that lives over E cross Jacobian of E bar, where over say some alpha here, so E cross alpha here, what you end up getting is this S alpha bar, but then over E cross B, you end up getting E natural bar like this.
Ah, I see. I think I understand. Okay.
And so then what you do is it's really you define some sort of like relative integrable system of some CM sheaves inside of this bigger surface here, and then so this is worked out in the paper, but you sort of define this bigger space of CM sheaves inside of this surface S. I guess this is not a surface anymore, inside of this three-dimensional variety S. And you define framings at the various sections, which degenerate appropriately in the limit as alpha approaches 0. And then it's these sheaves that you can identify away from alpha as the RS spectral sheaves, and at alpha equals B with the CM spectral sheaves.
I see.
So it's, but I mean, I guess pictorially, I like to think about it as just really just take an alpha to 0 or alpha to B kind of limit. Okay. So what are some benefits, I guess? So now I'm going to move on to some advertisements for why this is like at least a worthwhile way of thinking about things. So the original motivation is coming from some joint work that's still a work in progress with David Ben-Zvi and stuff that I started with Tom back when I was still at Illinois. So it was noticed by Krichever and Zabrodin that the poles of the so-called 2D Toda hierarchy, if you flow a general meromorphic solution to the 2D Toda system, the poles behave as if they were RS particles. So this is just kind of like a trigonometric version of something that was already noticed much earlier by Errol, McKean, and Moser, where flows of the KP meromorphic solutions look like CM particles. And so what you can hope to do is you can hope to understand this 2D Toda RS correspondence in this perspective. And the kind of cartoon diagram, there's a lot of cartoon diagrams in this talk, but the kind of cartoon diagram of how this would work is if I take P, the Poincare line bundle on E cross E check being the dual cubic curve, then I can define the Fourier-Mukai transform, and a relatively simple calculation shows that the Fourier-Mukai transform exchanges rank n vector bundles with length n torsion sheaves on the curve E. And then furthermore, if we apply the Fourier-Mukai transform to our two Higgs fields, eta 0 and eta infinity from before, this will correspond to something like a shift map for their two torsion sheaves. And so the details of which are still to work out is making this exactly precise, but the relations between eta 0 and eta infinity, the relations that were consequences of star, would imply that these things have various commutation relations between each other, which would hopefully match up with the Toda RS, or with the 2D Toda the 2D Toda commutivity relations between the various shift operators that exist in that theory. And so this is not kind of coming out of nowhere. The original motivation that Tom and David had for understanding the CM particle system in their perspective was in fact actually proving the KP-CM correspondence in a similar way. Okay, and so then the last slide here, this is, I should put a very big red warning. This is this reckless speculation about the double elliptic system that I'm very ill prepared to say anything about. And there's a lot of people in the audience who know this a lot better than I do. So, I'm going to defer any hard questions to them. But everything on this slide is more of stuff, that I've been daydreaming about more so than actually working out by hand and, it seriously. So like I said, this is very reckless speculation, but this perspective also, I think, could lead to a reasonable understanding of how the double elliptic system would work. And so if I take Y, just this product of elliptic curves, just like in the CM system where our space E natural and our space S alpha were birational to just the trivial ruled surfaces over the elliptic curve, you can hope that there would be some birational or maybe some isogeny, which would transform the surface, this abelian surface Y, into a more general abelian surface X, which it seems, by the work of Braden and Hollywood and maybe some others, it seems like the surface that you would really want is like these one end polarized abelian surfaces. And so the reckless speculation is even true at this very early stage of this slide, because I don't even know if such a thing is even possible. I don't know enough about abelian surfaces yet to really say exactly if the geometry works out in this way. But then the hope is that maybe you could define some sort of space of double elliptic spectral sheaves on the space X. And the candidate would be something like a completion of a space of Seiberg-Witten curves that we know exist from 6D compactified down to 4D n equals 2 theories, together with line bundles on those curves. And then using this birational transformation we had from the first step, there would be a hope that you could identify these RS spectral sheaves with something like a parabolic Hitchin description, or maybe a more general abstract Higgs bundle with values in an elliptic fibration with the space of the double elliptic spectral sheaves. And then again, more reckless speculation, but if all the choices were appropriately made, then in principle, there could be some PQ self-dual Hamiltonian system that pops out. And so, like I said, this is more of like a daydream than anything else, but I think this is kind of an exciting thing to think about, at least casually. And so, yeah, anyways, that's all I wanted to say. So thanks for listening.
Thank you. But on the last slide, there's actually, I wanted to comment, maybe Harry should know about this. They also worked out the bielliptic systems, which are not Dell systems. Mm-hmm. So maybe Harry can comment what is the difference, or how can we distinguish Dell from bielliptic systems?
I'm not quite sure what you mean.
I think there was a paper with you, maybe I'm wrong, of Mironov or Morozov, something about bielliptic.
Yeah, so I'm not quite sure what how that top line of what Matej says could work, because there is this extra parameter in the abelian surface that means I won't get it isogynous to a product of elliptic curves in general. Mm-hmm. And that's the mass parameter that appeared in someone else's talk. Yeah. So I don't think I can answer your question, answer its relation to bielliptic. Some of the curves that appear are bielliptic in the algebra geometric sense, but not quite sure in general.
Yeah, it's just we are talking about all these Dell things, and I'm just saying that there's other options too, and or am I wrong?
No, I think the game's open to, and that's why it's always useful for people to try and answer. Well, and as Simon said yesterday, what is the question that leads to all of these beautiful constructions?
Okay. Thank you.
So, Matej, what's the geometric meaning of PQ duality in this construction would be?
Oh yeah, that's a really good question. So I was hoping that this description could also offer some description of what PQ duality could look like. So I'll actually just kind of drop another cartoon diagram over here. So for example, if I look at the like RCM to, the trigonometric CM to the rational RS PQ duality, what I was hoping this could look like is that over here, this trigonometric CM system, well, it's going to live inside of this E natural space that's living over a nodal cubic curve. And a nodal cubic curve, so what this space could look like, so I have my nodal point here, which if I, so I have this nodal cubic curve and I map to the normalization P1 here with the 2 points mapping to the single node. And then I look at the surface, this P1 cross P1, which is the pullback of this E natural surface that lives over the P1, that lives over the P1, which is the normalization of my nodal cubic curve. And what I'll have is I'll have sort of two fiber divisors over the two points that map to the node, and then together with the section at infinity. And then what I was hoping was that if I just swap these two P1s, what I would end up getting is I would get a picture that looks closer to something like this here, where my section at infinity now becomes a section of a fiber over a point. And then my two sections over the points Q1 and Q2 now end up looking like my sections at 0 at infinity, which I have in the case for the rational CM system. And so then I could identify this. So this is like a surface that lives over P1, and then I can map it down to this cuspidal cubic curve. And so I was hoping that what ends up happening in PQ duality is something that's...
So here it looks like this fiber-based kind of...
yeah, exactly. But the problem is it's not, it can't possibly be this, because what ends up happening is if you look at, say, for example, frame spectral sheaves, what they'll do is they'll intersect over here and you have a particular framing, and they live in a particular linear system. And what ends up happening is that the picture really doesn't map you to the correct spectral sheaves over here. So what it really looks like is it looks like this very simple duality as written out like here, like this. What it looks like it's doing is it's changing say like an n particle one spin system into a one particle n spin system, which is by no means the correct duality.
I mean, it's not, yeah, good. So it's not the, okay, so I think it depends on the term, the name, sort of the way you call it. This is another duality that, you know, in string theory literature is also called, you know, fiber-based or PQ.
Yeah.
But yeah, so that, as far as I understand, so that's different from this, you know, bispectral or PQ duality, which sort of is the interchanging the action angle coordinates, right?
Yeah.
So yeah, so it's yet another, it's like a different, it's a duality in a different direction, so to say.
Yeah.
So it's still good to have it.
Yeah. So geometrically, it's not. So geometrically, the easy duality that you can write down is this fiber-based duality, I guess.
Yeah.
You can say something about what the PQ duality looks like if you identify various spaces with like moduli of or just like Hilbert schemes of points, and then you're looking at curves that map through particular points, but that's a little bit more involved. But this very simple duality here, I guess, is what the fiber-based duality looks like.
Yeah, I guess in that sense, the self-dual model would be, what is it, n plus one particle spin n or something like that. Yeah, so like
yeah.
So like it will be completely kind of self-similar as you do the rotation. Yeah. Okay, great. Yeah, thanks a lot. So any other questions?
Thank you.
I'm kind of worried that the next speaker has not showed up yet.
Then I have a small question.
Yeah, sure. Yeah.
Usual closure model system could be obtained as Hamiltonian reduction, from some metric system, and at least without spectral parameter. And with spectral parameter, it's like it will use this Hitchin system construction. Should we expect similar construction for Dell, or it is for some reason will be impossible?
I don't know. Yeah, I don't think I'm prepared to answer necessarily. What's kind of interesting is you can see the Hamiltonian reduction perspective of the lax matrix without spectral parameter in this geometric context, and it all boils down to at least in the rational and trigonometric case, it all boils down to descent data from P1 down to the nodal curve or the cuspidal curve, and or of like a n bundle here down to an n bundle here, and it turns out that you can identify this with like T star of GLN, like little GLN or big GLN. And this is where you can get the Hamiltonian reduction perspective, or even the quasi-Hamiltonian reduction perspective for the trigonometric RS. But in any of the elliptic cases, I don't think, at least I don't see how you could see the lax matrix without spectral parameter popping up, because there's no like simple normalization kind of map that exists like this.
Okay.
Great, thank you. Any other questions? Okay, then let's thank Matej again. It was a very nice talk.
Thank you.
Great, thank you. I'm gonna stop sharing. There
And
we
I
go.
think Yegor just joined. Yegor, hello. Yegor just made you the co-host.
Yeah.
Yes, you can share.
Yeah. Can you hear me? Hi.
Yes, we can hear you. Yes.
Oh, great.
You can share your screen, and then you can send me your notes. If you have notes or slides, the PDF, I can put it on the website.
Oh, I don't have.
Oh, you're actually gonna do the board. I see.
Yeah.
So
Right.
there's 3 minutes left. Let's take a break till 3
Sure.
minutes. Yeah. Okay.
Okay, great.
Okay, I think it's time to get started. Yegor, are you ready?
Yes, I'm
Sure.
ready.
Okay, great. So our next speaker is Yegor Zenkevich, and he'll be talking about elliptic Dingya-Harmiki algebra and elliptic integrable systems.
Okay, great. Thank you, Peter, for inviting me to give a talk and also for organizing this nice workshop. So I'm going to talk about some recent works relating the elliptic version of Dingya-Harmiki algebra or quantum toroidal algebra to elliptic integrable systems. So I will start not from the algebra, which is quite abstract, but from the other side of the correspondence, from elliptic quantum integrable systems, and not even elliptic. Let us start with a very basic example, seemingly not very relevant. So I will start with the simplest possible example of what is called Peary rule in the theory of symmetric functions. So Peary rule is the rule, well, it describes part of the ring structure in the ring of symmetric functions. So you can introduce, of course, different bases, different bases in the space of symmetric functions. Well, probably the most popular choice, which many of you know, is Schur functions. So Schur functions, you can say that they're symmetric functions in n variables, or you can say that they're functions depending on the power sums. So the power sums are just the sums of powers, and so these are Schur polynomials, and there are standard formula, for example, determinant formula for them. But then the question is, if you multiply two Schur functions, say I have S lambda times S mu, depending on the same Pn's, the same variables. So usually I will sometimes assume that n is very large. It can go to infinity. Sometimes it's possible to keep it finite. So for, of course, for finite n, not all of these S Schur polynomials are independent. So lambda cannot have more columns than n because of antisymmetry. But then if I suppose that n is sufficiently large, then there are no restrictions on lambda. Anyway, so if I multiply two symmetric functions, this is still a symmetric function. So and because as lambdas they form a basis. So by the way, sorry. So lambda is a Young diagram. So non-increasing sequence of non-negative integers, finite sequence. So I should have some kind of expansion of the resulting symmetric function, again in terms of S nu now. Okay, and I have some ring coefficients m. So these coefficients are very, in general, they're known, but they're complicated, and the algorithm for them is called the Littlewood-Richardson algorithm, and corresponding the Littlewood-Richardson coefficients. But the simplest parts of this ring structure, they can be written very explicitly. So my example, I will, in this talk, I will be concerned with the example when lambda is a single box. Or, well, later, maybe I will comment a little bit on further cases, but let's suppose that it is just one box. And if it's just one box, then, well, S corresponding to one box is just P1, the first power sum. So if I multiply this S1 box times S mu, let me suppress this Pn indices, they're the same in this formula. I get a funny formula where I sum over all diagrams, all sure functions corresponding to diagrams with a single box added in all possible ways. So I will write it as mu plus box and the sum over all addable positions. Of this box. Well, the meaning is obvious. So if I have mu, some kind of a diagram like this, then where are edible positions are here. So this one is edible, this one is edible. So in total, in this case, I have 5 edible positions. So edible, which means that when I add the box, I still get a Young diagram. So the important, well, of course, it's important that I sum over all edible positions, but another piece of information in this formula is that there is a coefficient 1 here in front. So there are really, in this case, these numbers n, they're all 1, either 1 or 0. So if the box is in an edible position, then it's 1. Otherwise, it's 0. So this formula doesn't look very relevant for any sort of elliptic integrable systems, but it turns out that it is really. So there are 2 important generalizations. One of them is immediate, and the other is a little bit less trivial, but still, I would say, straightforward. So the first one is the generalization to Mcdonald polynomials. So we know that the sure functions, they can be deformed into Qt-dependent system of elliptic functions, Mcdonald polynomials. So there is a deformation of this S lambdas into n. So, well, there are, again, various ways to define m lambda. There are no determinant formulas, unfortunately, but there are many more ways. So you can find them by orthogonalization with respect to a deformed scalar product. But by the way, let me introduce the scalar product. So here are sure functions, and they are orthogonal with respect to the following scalar product. So if I take Pn dagger to be n d by d Pn, then I can write. Well, okay, let me erase a little bit of this. Let me retain this central formula. So then I have S lambda depending on Pn dagger times S mu depending on Pn. And I have to act with this differential operator on this function. And then at the very end, set Pn to 0. And this is going to be orthogonal. There is delta. So this is what I call a sure scalar product. So this that's mu. So this is so here I can say that this Mcdonald polynomial, the Mcdonald polynomials, they are orthogonal, but with respect to a deformed scalar product. So there the scalar product differs in the following way. So I have to add T and Q. Well, naturally, because I have a QT deformation, so I have to add Q and T in the mix in my definition of the conjugation. So otherwise, it's the same. And then this will give me a Mcdonald scalar product. and this is still delta. So Mcdonald's polynomials, well, they are enumerated by the same set of partitions, and they are still linearly independent of each other. So they also form a ring, a basis in the ring of symmetric functions. So naturally, well, it should be possible to compute at least some coefficients, some well, deformed Littlewood-Richardson coefficients in this formula. So in fact, it is possible. So the formula is as follows. M corresponding to one box. So M corresponding to one box is the same as P1. So this is still P1. So this one is P1, the first power sum, and this one is still P1. So this one doesn't change. However, all the other M's, they do change. And here there is, again, a sum over all edible positions, but let me write it in a little bit different way. So I will write it as a sum over I. So let me draw again my partition like this. So my I will go in this direction. So I'm going to put my boxes in all possible positions here. So this here is the length of my diagram. So this is my diagram. Here are the parts of my partition. These are the heights of these columns. I don't know. There are many different conventions on drawing Young diagrams. The Russian one, the French one, the English one. Unfortunately, I don't know which one is this, but sorry, but I will use it. So I sum over all positions I from 1 to the length plus 1. So because eventually I'm going to also sum over all these edible positions, and the last edible position is here, which is L plus 1. But the important deformations comes here. Instead of 1, I get a non-trivial coefficient here. So the coefficient here is J, a product over J less than I of the following special, of the following curious function. So I have a very particular function here, very particular, taken at very particular points. Times, here I will say that I have a box put at position I. So this means that, so here, for example, I have, this one is a box at position 2. Okay, so the difference is in this function psi, over which I have to multiply. So what is psi? The psi is the following Qt deformed function. It is 1 minus x, 1 minus qx here, 1 minus tx, 1 minus q over tx here in the numerator. So as you see, if I take t equal to q, so if I degenerate back from Mcdonald's polynomials to Schur functions, then this psi becomes trivial, right? Because, well, everything, these two cancels, so this cancels with this one cancels with that one, and I get back a unit coefficient. Well, you can ask, oh, okay, I have here, I don't have a sum over edible positions, but over seemingly over all possible positions where I can play this kind of Tetris in any way. Even the forbidden positions are allowed, but in fact, so because of this curious point at which I take this psi, it actually prohibits putting this I into anything apart from the edible position. You can see that there is here there is here something Qt dependent. So, well, for example, you can say, what if I have some position let me denote it. So those I denote by a cross. So this one I will denote by a dot. So this is a kind of precarious position, which is forbidden actually. So why it is forbidden? Because here I have some, I don't know, mu I, and the previous one is mu I minus 1. Sorry. Okay, I have to write it more clearer. So here is mu I, and here is mu I minus 1. So suppose they are equal, then it is forbidden. That's precisely when this extra box cannot be put here. So what happens to this function psi? Well, with this function psi, I have there is a difference between I and j. So j is I minus 1, but then the mu's are the same. So I have to take psi of t, right? So sorry, t inverse. Yeah. So okay, I'm slow today. So t minus 1. So which means plus. So which is psi of t inverse. And you see, psi of t inverse is 0 because of this term in the product. So this box is truly forbidden, not just by my well, by the prescription in the sum, but instead because this psi simply vanishes. So I can extend the sum to all i's as written here. Now, what this formula tells us, the deformation formula, deformed formula. Well, actually, this formula is related to an integrable Hamiltonian, a quantum integrable Hamiltonian. So which one? Of course, since we are dealing with Mcdonald polynomials, the only possible answer basically is something related to trigonometric Ruijsenaars system, Ruijsenaars-Schneider system. How does it work? So I have the first Hamiltonian of the system. So I have a Hamiltonian H1 acting on functions of some variables which I denote by y. Suppose there are n of them. And the formula for this Hamiltonian is that it is a sum of, it's a difference operator. So it's a sum from 1 to n, product over j not equal to I, yi minus yj over yi minus yj. And here I have a shift operator acting on this function psi. So what this operator does is it rescales the ith variable here, right? So this is the Hamiltonian. Okay. This is the quantum Hamiltonian, and well, the eigenfunction of it are Mcdonald polynomials, but that's not what I'm going to look at it in a little bit different way. So I suppose that this operator acts on the labels of Mcdonald polynomials instead of variables. So you see here the variables in my polynomials, they remain the same throughout the formula. So I'm not going to act in this particular case, I'm not going to act on the variables of my Mcdonald polynomials. I'm going to act on the labels, as here you see. So I have an action on the labels, and it turns out that this one, so this sum and this sum, they are precisely related. So you can ask, well, there are there are questions, right? Because, well, first of all, the formulas simply don't match because, well, there is
second formula is not the eigenvalue problem, right? It changes the partition, so it's like the raising operator.
It is an eigenvalue problem. Again, if you look at it as acting on the labels. So my eigenvalue here is P1. So this eigenvalue again. So the labels in this formula. Let me say that. Look at it as a problem, as an operator, an eigen problem.
Where is P1 on the right-hand side?
No, P1 is on the left-hand side. So I have an operator in the right-hand side. I have a Hamiltonian. Well, let me say it's kind of dual Hamiltonian, which acts on labels of my Mcdonald polynomial M mu. So mu are my variables. So it's a Hamiltonian in mu, in quotation marks.
I see. And then, okay, I understand. Yeah, so it shifts. Okay, I see. Okay.
So that's precisely the eigen problem I want to view. So I have, well, there are two things to address here. So first of all, it acts on the labels. So I have to somehow relate my variables here y to the labels. So yi are related to mu I. So more precisely, I have to identify yi with q power, mu I t minus I. Okay, so you see these variables here, which sit in the functions, they're precisely yi. And because my Hamiltonian is a difference operator, then this difference operator corresponds to shifting the variables. So on this yi, I have my shift operator acting, and it corresponds to mu I going into mu I plus 1, or mu I plus a box. So I have, so my shift operator, that's precisely what is written here in the label. Now the last remaining problem is here, because here I have a product over J not equal to I of something. So this I can of course rewrite like 1 minus t yi over yj, 1 minus yi over yj, right? But it's not psi, because you see I have only half of psi. So my psi, I have this piece of my function, and I lack, oh, I have another color. I lack this piece. So to get this, well, there's two problems that of course cancel each other, because I have to modify, I have to rescale my function psi a little bit. So I have a clever conjugation transformation on this.
Sorry?
My A. Sorry?
Simple question.
Yes.
Igor? So if you write the other half, so what you're saying is just you have a half of the product in this lower formula, and you have almost the full product. So you're saying if I just write it for j not equal to I, you're missing. You need to add the other half. So it's just not there.
So you see, I have sort of, if here is I, right? Here is my total interval from 1 to n. And in one formula, I have a product like this. So I is missing, but I have a product from 1 to I minus 1, from I plus 1 to n, over, say, like a single piece, like here. But in the second formula, I have a product like this, like taken 2 times, right?
So I have
and
to
there's
do
no
something.
Symmetry. There's like I'm used to the fact that
Yeah.
usually there's symmetry, but here it's a bit different, slightly.
You're pretty close. You're pretty close to the right answer. It's not exactly equal, but the Hamiltonians are related by conjugation with a cleverly chosen function. So let me erase this part.
So Yegor, you can also get the other. If you take the other TRS Hamiltonians, we'll get more identities this way.
Yes, it will be higher Peary rules. Again, that was basically the next thing I was going to say, is that there are higher Hamiltonians and there are higher Peary rules, of course, because you can say, what if I have M corresponding to diagram 1, 1, 1, 1, 1, or as it is called 1 power k. So these are the same as Schur functions, and also they are the same as what is called elementary symmetric functions. So they are antisymmetric, basically antisymmetric Young diagrams, corresponding to antisymmetric Young diagrams. So there is still the same formula, a little bit more complicated. You have more products, and there are some. I can write the formula a little bit later. Just let me finish with this conjugation, and then I will write the formula. Yeah, there are higher Peary rules and corresponding to higher Hamiltonians, of course. So here I have to invent a function. So let me call. So here I call this Hamiltonian as I did H with this funny thing with this V check H check. So to relate H check to H, I have to conjugate it with a funny function of the variables y, which form is like this. So it depends on all y, and it's a product of I less than j, yj power beta times the following function, yi over yj. It's an infinite Bach-Hammer symbol. So the Bach-Hammer symbol is an infinite product. And I have to take this whole product. So if I conjugate with this one, well, I'm not going to do the technical exercise. As usually people say, it's easier to do yourself than to bother with the details in the talk. So this clever function, it spits out exactly this piece, this missing piece, while canceling this extra piece. So that's exactly what it does. So if I act with the shift operator on my function f, it again gives me my function f back times a certain product over j not equal to I of something. So, and this special something is exactly what cancels this one and this one. So the formula is like this.
Sorry, Igor, I don't see the formula because of the glare. There are braces. There are braces. Y comma.
Here. Okay. So let me. I'm sorry. I think I cannot do anything. So let me just read it.
Just tell me what.
Product of our. Oh, sorry.
What are the braces? The brackets.
Yeah, there are the brackets over everything, and there is a product over product of yj power beta and the ratio of two Bach-Hammer symbols.
One is they're not some special symbol. Okay.
No. It's just okay. Yeah, I'm using them to just for larger brackets, huge brackets. So okay. So these two Hamiltonians are related, and we know now that Peary rules are precisely an incarnation.
What is the beta?
Sorry?
Beta?
Right. Sorry. So beta is logarithm t by logarithm q. So that's the power. So
is it the modulus or something? Sorry,
It's like if I think of T and Q are period, if it's like elliptic, if this is an elliptic whatever effect, like omega 1, omega 2 in the torus, this is like a tau, or I'm wrong?
I don't think so. I think it's, well, you know the story about epsilon parameters and this omega deformation. So that's the ratio of omega deformation parameters.
Epsilon 1, epsilon 2.
I don't think you can view it as a modulus. Maybe you can, but that's this I don't understand, and I don't know a way to understand it in this way. So.
Yeah, probably not. I just I just was thinking about this elliptic stuff as Q and T could be something else.
Okay, so in a moment we will move to elliptic, where we will have an elliptic sort of variable. So what I wanted to finish with what I promised, the formula for higher Hamiltonians. So the higher Hamiltonians for well, the original Hamiltonians for quantum trigonometric Ruijsenaars-Schneider system we know. So there will be a product. Okay, so there will be this HK. Let me try to squeeze it in here. And there will be a sum over a subset of integers from 1 to n. And there will be a product over J, well, a product over I belonging to this subset, and the product over J belonging to everything else, basically 1 and minus I, without I. A product of the same stuff, the same function, and there will be just a bit more difference operators here. So there will be a sum of these difference operators for all I here. So there will be more shift operators, but otherwise, and there is a funny coefficient here. Well, not very relevant, just to be precise. Kk minus 1 divided by 2. So this is the definition of the Hamiltonians, and then they correspond to Pierre rules for this Ek for Mcdonald polynomial. So let me write this. If I have a Mcdonald polynomial corresponding to 1 power k here,
sorry,
and I'll multiply. Right.
Just to be sure, so you're summing over all possible subsets, including like 1, 1, 2.
A subset. So no. Sorry. Of k. Well, the total number of elements should be k, and it's a subset in the sense that, well, the numbers cannot be the same. So it's a subset in the sense that, well, you know, a subset.
So I need to pick. I need to pick
different integers.
K numbers, k different numbers.
Yeah, right.
From the 1 to n subset.
Right. So if you have, okay, let me give an example. If k is equal to 2, you have to take a sum over I1 less than I2. So that will be your sum, right? Up to n. So that's the description of it. But well, I could have written it with the sequence of I1, I2, etc., Ik, everything, like the strict inequalities. Okay, so let me write the formula here. So again, there are the PNs. The PNs are the same. And here I have, let me write it precisely in this way. Because here it is more convenient. It's I1, I2, etc., Ik, times there is a product here of J1 less than I1 of psi. Let me just. I think I've explained that why I is completely equivalent to this. I will just use this definition of yi here because it's more compact. J1, and here there is a product of J over J2 less than I2, but another constraint is that it shouldn't be equal to I1. And there is another psi here, J2, etc. Well, now you understand the pattern, because I1, I2, etc., Ik, so they're again up to n. So they sit somehow like this. I have my interval from 1 to n, and I have here I1, I2, Ik. So my product over J, so the first J goes here, so this is J1, and the second product over the second J, J2, goes here and here. So this is J1, J2, and J3 naturally, well, it skips every previous I, as you can see here. So I take this multiple products, and this is just obtained from this Hamiltonian with conjugation. Blah, 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 there is this product. And finally, in the end, I hope you can see it, there is this product, there is an addition of several boxes to my partition. Okay. So this is precisely the shift operator I have here. Yeah, the product of the shift operators I have here acting on psi. So there are higher PRE formulas. So these are higher PRE rules or formulas.
So I guess you're going to tell about the duality, right, between regular operator and the one that acts on indices, right?
Right. There is a duality, of course. Let me first talk about elliptic stuff. So, well, okay. Let me have a kind of a little bit of an how to call it, an interlude. So we have a duality, a PQ duality. Between.
Sorry, this is almost not visible.
Okay. Let me. So it's not visible because it's like this is better?
Now it's better, yes.
Okay, good. So there is a PQ duality between mu I and xi. So in which sense? Of course, again, in the sense of this y variable. Basically like this. And then I can switch between these two. So there are Hamiltonians which act on mu, and there are Hamiltonians which act on x. So when they act on x, they have the Hamiltonians with this
and I think that I understand now. So this is the avatar of the 3D mirror symmetry when you have interchange the quantum Kähler parameters and equivariant parameters, and then specify them to this locus that you said. Okay, good. So the i's become q to the mu I t to the minus I. Great. Yeah, I understand that.
Yeah. Okay. So you have self-duality. So now I'm going to talk about elliptic stuff. So in the system here is self-dual. So H check has basically the same form as H, apart from this conjugation, which is harmless naturally. It's a conjugation. So the elliptic, the funny part, which I'm going to talk about, the funny part of this PRE business, so is this elliptic PRE rule. And it is about a ring of polynomials. Again, this is about elliptic symmetric functions. Elliptic in a sense of elliptic dependence on Q and T. So on Pn, it's still polynomials. So polynomials in Pn, but they have an extra variable omega, which will be an elliptic modulus. So this will contain some theta functions of Q and T. something like this, like coefficients. So this is a sort of elliptization of Mcdonald polynomials, because in Mcdonald polynomials, you had something like 1 minus q, 1 minus t in the coefficients. So here you would have the thetas. And there is a list of, well, you can define these polynomials using some explicit formulas. This is what is called the Naomi-Shiraishi series. And then from the series, by a certain truncation, well, it's a non-trivial way to get these polynomials, but at least it's algorithmic. I'm not going to talk too much about how to get these polynomials exactly, but there is a way. It's a certain special locus of the series, and then certain truncation, and then you have to take a certain have to take a conjugation, what we call conjugation. I will talk a little bit later about it. So for now, these are sort of God-given set of polynomials. Okay, we somehow know the definition of certain objects very explicitly, and like one can compute them up to some orders. Well, not unlike Mcdonald polynomials, where you also can, basically the practical way to operate with them is to compute them up to certain orders and then do all your stuff with them. So these elliptic polynomials, surprisingly, they satisfy elliptic Pierre rule. And well, to write it out here is kind of, it becomes kind of boring. But believe me, it's a very non-trivial rule. If you are going to just invent some polynomials with some omega dependence, with a bunch of theta functions, then it's really difficult to cook up anything which satisfies something similar to this. So the formula is exactly the same, apart from a different function. So I'm writing it over this Mcdonald formula to emphasize that the formula is very similar. It looks kind of the same. But this function psi is now a new function, psi elliptic. So psi elliptic is a naive elliptization of this psi. So this psi elliptic of x is the ratio of theta functions, like this. So my theta functions are Jacobi theta functions. So theta omega of x is omega.
On the left, right?
Sorry?
I mean, you also have on the left, not m, right, in your formula. You just forget to replace one of the.
Right. Thank you. Sorry. Right. Like this. So that's sorry. That's the standard definition. And I have some elliptic coefficients. In fact, if I really believe in this, even in this form of this rule, if I have, because there are many ways, as you know, there are in Mcdonald polynomials. Well, this little Wood-Richardson coefficients, they're complicated. If you look at them at first sight, they become some mess, really. So if you put them in this form, then you can, well, conjecture that there are polynomials which satisfy this one. And then either, well, of course, you know, there are different ways. The first way to obtain it is to guess that this is really true and substitute the known polynomials into it. But when you think about it, you can do it vice versa. Like you can say, okay, let me start with the simplest polynomial. Let me define this E corresponding to one box. Let me say that it is P1. And let me put an additional simplifying assumption that E corresponding to antisymmetric diagrams are again not deformed as in Mcdonald's case. So they are still sure polynomials. Then I can use this rule to obtain as a recurrence relation. Because you see, if I know lower polynomials, then here in the right-hand side, I know the polynomials corresponding to higher diagrams. So in this way, I can like turn the crank of my machine backwards and compute this ease from these assumptions. So the assumptions basically is this one, and then the second one is that this rule holds. So if this rule holds, I obtain some polynomials, and they also, of course, the other way around, they also coincide with the truncation of the series, truncation and conjugation of the series.
Okay? I have a question. So that looks like the twisted version of the elliptic RS Hamiltonian, right? So if you twist away this omega theta of Q divided by theta of Qx, right? Now, in what I know, the eigenfunctions of elliptic RS are generally Laurent series in X. So you can only truncate it from one side. I don't see how you can get a polynomial this way.
It's not a look. It's not a again. So it's a polynomial in P. So it's a reverse. Well, it's a dual problem.
It doesn't.
So P
so
are labels.
So are you saying that you can? So this elliptic. Are you saying that elliptic polynomials are truncation of this elliptic series? What we call with Shamil, like the. So these are the eigenvalues, eigenfunctions of the elliptic RS model, right?
So they are eigenfunction in labels, as I said with Mcdonald.
Labels in this dual frame, you can actually okay, I see. Yeah, sounds good.
Yeah. So this is the next thing I would like to say is that when I have this rule and when I have this funny polynomial, they're polynomials in P.
It's 3 minutes left till your technical time, but you can take till maybe
okay.
Let's take maybe 10-13 minutes. Will that be okay? But try to sort of.
Okay. Yes. Sure. I will stop in 10 minutes. Good. So as you can see, so this leads to an elliptic RS Hamiltonian acting on labels of E lambda. So P's are eigenvalues again. So this P1 is an eigenvalue of this problem. And again, I have to conjugate a little bit to conjugate with some function f a little bit. So this doesn't spoil this picture. Of course, there is this conjugation. The next question is what? Well, and the one of the crucial questions is we know that there is a duality between this elliptic RS and this there is this PQ duality. There should be a PQ dual system, a dual elliptic RS system, which should now act on P, not on the label, but instead on the variable. It is just the same as with the Mcdonald polynomials. I have to have some Hamiltonian H, say, I don't know, H check, which acts on Pn. So presumably this E's should be, there should be some eigenfunctions of a dual elliptic RS system. So one can test this hypothesis because there is a conjectural dual ERS Hamiltonian introduced in the works of Peter and Shamil. So we use the form of this Hamiltonian. So there is this HKS Hamiltonian, and there are many forms of it, but it's important that there is, the principal construction is that there are these operators, which is a series. So there is a sum of with elliptic modulus, etc. And with this, so I'm not going to write it all. Times something times the shift operators. Okay, let me call them x. And then one needs to, so to obtain the Hamiltonians, one needs to take a ratio of the coefficients. So this one becomes a series of n un, and one to get an nth Hamiltonian, one needs to take a sort of ratio of two terms on this series. Well, we use a little bit modified prescription, which is equivalent. So first of all, we use we say that the Hamiltonians you can take just a ratio at two different points. So you have Hamiltonians which depend on u and v. So it's in principle it's a series in u and v, h and m, but only a finite number of them are actually independent. Just as here, because here n is it's a periodic in n, so only a handful of them are independent. So here it is the same, and the prescription is actually equivalent. It's let's say it's a modified Hamiltonian. Another useful way of writing this Hamiltonians is to write this all in the form which was shown in the works of Andrei Zotov and Andrei Grekov. So we have this. It's a determinant form. So I have a van der Monde determinant here times a certain determinant like this with theta functions of shift operators. Sorry. Anyway, it's a determinant function, and it's very convenient for acting on symmetric polynomials because this determinant is actually triangular in the basis of monomial symmetric functions. In m lambda basis. Well, this is another symmetric function basis. So one can ask what are really the polynomial eigenfunctions of this Hamiltonian. And it turns out that they can be using this rule that they can be using this form of the Hamiltonian. They can be computed. So that's the last thing I'm going to say is their so-called polynomials p lambda of qt and omega, depending now on x or on pn if you wish. And what are they? So the idea, the natural conjecture is that they are equal to a lambdas. So they're the eigenfunction of h acting in x. So h acts in, now not on the label, sorry, h lambda, ks, h lambda, p lambda of x. So they are a function of Hamiltonian acting in x now. So probably they should be dual of dual to the function of the dual Hamiltonian, right? Well, wrong. This is not the case. But there is well, they are almost like this. This is almost true in a sense that it turns out that p lambdas. Well, okay. The following holds. So if I take p lambda, exchange t and q, take a transposed diagram, and take -1 power n plus 1 pn, and take its Schur product, Schur scalar product with E, Schur. not Mcdonald, not deformed. So this is the original scalar product which I described already. So this is going to be orthogonal. So E lambdas are not orthogonal to each other with respect to this non-deformed scalar product. Well, that's not surprise. Even Mcdonald's are not orthogonal with respect to this scalar product. However, there is a dual kind of a dual system of dual bases, right? If you have non-orthonormal basis, you can define a dual basis like this. So you define it, and then these bases, these dual bases, it is the eigenfunction of this dual Hamiltonian. So that's the bottom line. Thank you very much for your attention. Sorry for running over time.
So Pn here, when you say it's like sure, you mean that this is a Pn is just the derivative. It's a sure you're using a sure.
And d by dPn. So you act with this, set all Pn's to 0, and that's your scalar product. There are nothing in front here. So you don't have anything like this. No funny business.
So yeah, let me try.
Just a comment. This is the notion of bi-orthogonal functions that you are really making use of. To
okay.
Yeah, it's known in more contexts that this is a natural generalization to trade the concept of orthogonality for bi-orthogonality in the way you just explained. Although I'm pretty sure that this way of doing it is, I have not seen it before for this particular case, but the notion that you have these two bases that are bi-orthogonal, as it's called, it has been around in the field for quite a long time already. You may not be aware of it, I'm not sure.
Okay, I'm not aware, sorry. So I would be really glad if you could send some reference, because I'm really interested in this. And yeah, okay, thank you for pointing this out. Thank you very much.
Well, I'm pretty sure that Slava in his next talk will actually mention this concept of bi-orthogonality, because in his setting it also walks around. So
I will not mention it, but I can comment. I would suggest to take rank 1 case, and this is corresponds to Q ultraspherical polynomials and the bi-orthogonality.
The case of is really very degenerate. I don't think you can learn much.
And so there may be something in one dimension or in one variable case, so that you can see better what's going on in this picture. But
yeah, I agree.
Okay. Yeah, thank you. So
that would be very useful.
I will look into that.
Would be very useful to look at the rank 1 case.
Yeah, but as you all know, in rank 1 case here, it's very degenerate in the sense like all these dualities, they're the same thing. It's kind of a problem.
But still you're working with wave functions. So in terms of wave functions, you can see something. So it's not completely trivial in terms of wave functions.
Yeah. So
maybe you're suggesting that the wave function they will coincide in this. That P and E will coincide, but it's question to Yegor.
I fear that both orthogonalities will be the same in rank 1 case.
I mean, if you insist on orthogonality, then you get out of this picture. Then you can no longer write the eigenfunctions in terms of just polynomials. That's already well known for the operators where you do not discretize. You have discretized them. And that makes it possible to sort of recurrently define the eigenfunctions in terms of polynomials. That's a very neat idea, but it would not give you the eigenfunctions discretized that you need for the non-discrete, for the continuous case. You see?
Yeah, I see. So yeah, it all rests on this difference, on the fact that it is a different story. I see.
Yeah.
Okay. Anyway, I have to look into the rank 1. The rank 1 case may be illustrative. I have to look into it in detail, maybe.
Mhm.
Good. Great. So I think we need to go to the next talk and maybe continue discussion over email. Thank you very much, Yegor.
Okay.
Great.
Okay.
So
Thank you.
speaker is
Yeah.
Slava. Slava, you ready? You can share your screen. We have.
Yes, I'm ready. Let me see. Is this one? Yes.
Yeah, we can see it. Yeah.
I'm ready.
Okay, so our next and last speaker of the workshop is Slava Spiridonov, and he will be talking about from elliptic hypergeometric integrals to complex hypergeometric functions.
Thank you. So I will not be talking about bi-orthogonal functions. It will be most completely about integrals and some equations for them. And my starting point is the set of top special functions of hypergeometric type, namely transcendental hypergeometric functions, special functions which are called elliptic hypergeometric integrals.
Slava, could you turn up your volume?
Yeah, that would help, I think. Yeah.
Okay, I will just take closer the microphone.
That's better.
So, okay, it will be about elliptic hypergeometric integrals. Why integrals? Because series form of these functions is not well defined, only integral representations work. So that's why it's mentioned exactly integrals. But to the lower level special functions, it is possible to work both with the series form and integral forms. Okay, let me start from the very characteristic function, which is an elliptic analog of the Euler-Gauss 2f1 function. I guess everybody knows what is this. And it has the following form. It's the V function, which was mentioned in the talk by Shlomo. You have two infinite products, which are defined here in front of the integral over the unit circle of positive orientation. And then you have in the numerator the 16 elliptic gamma functions, plus minus. It means that you have actually a product of two elliptic gamma functions. This elliptic gamma function is defined here. You saw already several times during the talks. And in the denominator, you have two elliptic gamma functions of this form, and this is the measure for torus. What you should do, you should impose on this 8 parameters Tj the balancing condition, which has the following form. The product of them is equal to pq squared. And this constraint is important when you choose the contour of integration as a unit circle. Then this contour under this constraint separates very neatly the sets of poles of this integrand, which is written here. So that's the definition, which I introduced long ago now. And this elliptic gamma function satisfies this Q difference equation of the first order with the theta function in front as a coefficient. And the theta function here is defined as the product of two infinite products. And then it is a kind of truncated Jacobi theta 1,1 function. Okay, and there is the very nice, very simple inversion relation, which is very trivial to see just to looking at the numerators and denominators of this function in this double infinite product. And so if you impose such a constraint of this type on this function, namely you choose T8 as the PQ divided by T7, then you see here, you get exactly this type of product twice. And T7 parameter drops out completely. You have 6 parameters which satisfy the product of 6 equal to PQ. And then this guy becomes computable. You have exact expression for that. And here's the exact answer, which I have found 21 years ago now. And that's actually the very beginning of this set of the transcendental special functions and of this new class at that time of special functions of hypergeometric type. And now I'm going to talk about some limits from this V function, from this elliptic level down, very deep down to the set of functions, which nobody was discussing in the context of integral systems and related things. So it was missed, namely complex hypergeometric functions. But before going to that, I will mention the set of applications of this V function or general class of elliptic hypergeometric integrals. So this V function is a special eigenfunction of n equal 1, 1D model, which is a BCN root system generalization of the Ruijsenaars model. And it's very, you have to choose a special eigenvalue. You have to choose a special set of parameters for this Hamiltonian. And then this V function becomes this eigenfunction of this Hamiltonian. And there is also a similar picture for BCN extension of this V function. I will not talk about that. I will talk only about rank 1 case. But it is also emerges in the set of eigenfunctions of BCN 1D model. Okay, second, actually, the most important application of this V function is within this theory of supersymmetric, four-dimensional supersymmetric field theories. It describes superconformal indices, which count BPS states of with the following setting. So gauge group is SU2, flavor group is SU8 for the V function, or SU6 for the elliptic beta integral. And the chiral superfields of these models should be belonging to the fundamental representations of both these groups. And in this setting, this is nothing else. This function has the symmetry. So you see, this is the contribution of gauge fields. This is the contribution of chiral superfields. And altogether, this is a superconformal index of one particular Zyberg model, Zyberg's QCD, supersymmetric QCD. And he suggested the duality, Zyberg duality. And in this context, these V functions obvious the wild group symmetry for the exceptional root system E7. And that is exactly the symmetry which describes the Zyberg duality at the level of BPS states or at the level of superconformal indices. And this guy, the elliptic beta integral evaluation formula, proves the confinement conjecture in this SU6 flavor group supersymmetric field theory model. And this conjecture was done also by Zyberg. And so this is the, in a sense, mathematical proof of the simplest confinement phenomenon in this particular set of BPS states. And this relation to Zyberg duality was noticed by Doyle and Osborne also now long ago. In statistical mechanics, the same functions emerges in the context of star triangle, star-star relations, and they define top solutions, currently top solutions of the Yang-Baxter equation, which guarantee integrability of the models lying behind these relations, in particular 2D type of Ising model or 1D Heisenberg type spin chain behind this Yang-Baxter equation. And in this context, the Zyberg duality is exactly the integrability condition. So for the Zyberg duality guarantees you existence of these equations which are needed for the integrability of the system. So it has very nice applications in within this spin system, integrable spin systems. And here are the references very fast to the literature on these applications. And now I go to the technical things. First, I would like to describe how this function is degenerated to the trigonometric level when you fix Q and take P goes to 0. Using these relations for the elliptic gamma functions, if you just keep Z and Q fixed, then you can set immediately P equal to 0 and get this infinite product. Very simple limit. If you scale Z by powers of P alpha, when alpha between 0 and 1, then the limit is very trivial. It goes to 1. And if you take the P, first power of P, then you get opposite infinite product. So if it was in the denominator, it's in the numerator. So very simple limits. And what I do as a simplest example, I clean the balancing condition. I take a rescale TG, so I parameterize them in the following way, and the sum of exponents alpha j take to 1, so that the product of j becomes q square. And then assuming this type of values of alpha within this parameterization and fixed these parameters j, then it's very easy to take the limit and to boil down to the following integral. So V function becomes integral unit circle of the following set of infinite products. So 6 infinite products, 12 infinite products in the denominator, and here you have 4, 6 here. So it's split because some come from here, some come from here. For very special choice of the parameters gk in some limiting cases, this is nothing else as the SIG-J symbols for the SLQ2 quantum group or Askew-Wilson functions, so well-known things. And you can simplify these functions further, go up to the level of Euler integral representation for F21 function. Very nice thing that it is in the at the bottom of this integral representation. Next is the rational degeneration. Now to the previous formula, I applied the limit q goes to 1. The q to 0 is very trivial limit. For that, I need to notion of the Jackson's Q gamma function is defined here. Why it is nice? Because now the functional equation has this form, and the limit when q goes to 1, it goes to the standard Euler's gamma function. And long ago, Karminder showed that this limit is actually, when q is real and goes to 1 from below unity, this limit is uniform on compactor. And Erkrein showed that it is true for complex values of q, provided the limit is taken from inside the unit circle, from the unit disk, I would better say. So this is very important because using this uniformity, I can now apply this limit to the previous integral and rigorously prove the following integral, the following limit for the integrals. So I substitute the integration variable in this form, the parameters in this form with this summation of exponents again to 2, replace infinite products by this Jackson's Q gamma function so that the limit is well defined. And after taking the limit, I will come to the Mellin-Barnes type of integral when you have a contour of Mellin-Barnes type separating the necessary sets of poles lying to the left and to the right of the contour. And here is the structurally, it looks almost the same as previously, but now we have Euler's gamma function inside this integral. And you have here some factor, which is divergent factor, so the limit is not so simple. You have the divergences involved, and this integral can be taken boiled down up to the Barnes representation for 2f1 functions. So you see from one and the same function, this elliptic hypergeometric integral, you can go down to both representations of the 2f1 function, which are known in the literature. Now it's more interesting limit, the hyperbolic degeneration. You parameterize the parameters Tg in the elliptic hypergeometric integral in the following way. P, Q, Z, T all go to unity because this V, which enters in the exponents, goes to 0. And as shown by Simon Ruijsenaars, you have for the elliptic gamma function the following limit. You have blowing up factor here because V sits in the denominator of the exponential of the exponent. And here you have another gamma function, which I would be calling the Faddeus modular algorithm because it emerged in the two-dimensional conformal theory at the time. And in the terminology of Ruijsenaars, it's a hyperbolic gamma function, and it has the following definition. So you have exponent of the Bernoulli polynomial of the second order, which is written explicitly here, and this gamma small without indices is the ratio of two infinite products. Q products, where Q, you see bold Q, is now exponential of a ratio of omega 1 omega 2, and Q tilde, it's a particular modular transform, it's minus 2 pi or omega 2 divided by omega 1. So you have infinite product in the numerator and infinite product in the denominator. This representation is defined when Q and Q tilde are both modules less than 1, but there is the integral representation for the same function, which is well defined in a wider region of values of Q. In particular, if you take positive for these quasi periods, when Q is modulus 1, then for this region of U, this is very well defined integral, so function is very well defined. And Reins in 2006 has shown that this limit is uniform on compactor. And this is very important because on the next slide, I will be applying this limit to the elliptic hypergeometric integrals, and it will give me the rigorous definition of all the limits. So before doing that, I will need the Dedekind eta function defined here. And it has this modular transformation property, which is very useful for defining the asymptotic behavior of this infinite product when tau goes to 0 or Q goes to 1. Okay, what's the limit? So V function for this parameterization, V goes to 0, has the blowing up factor of some very simple form. And here's the hyperbolic hypergeometric function. Having this now 16 Faddeus quantum dialogarithms, modular dialogarithms, and 2 of them in the denominator or hyperbolic gamma functions. So this is again Mellin-Barnes type representation because this contour should separate particular sets of poles sitting in the integrand. And this is the condition. If you want to have this imaginary axis, then you have to impose this condition. And the balancing condition now became this relation. Sum of g's is equal to 2 omega 1 plus omega 2. Again, for special choice of parameters, this is an eigenfunction of n equal. Here what I want to say. So for special choice of parameters, you can reduce to a smaller number of variables g, and then it becomes the eigenfunction for the n-equal Hamiltonian or hyperbolic Ruijsenaars model, which was considered by Simon in '94. Or in a different setting, but it is the same. It's 6G symbols for the Fadeev modular double quantum group to direct product of two SLQ2 quantum groups, but with different moduli, parameters Q and Q tilde. That's why it's called modular double. And these 6G symbols were computed by Poisson and Teschner, and so this is these symbols are described by this function, and it sits here as a very special limit. So I just mentioned the things which are, I'm sure, known to the audience. So reminding now this the parameterization. Now instead of bold, I use standard Q and Q tilde. Then substituting for this gamma 2 function through the Jackson's Q gamma function, and you can write this expression, and you see that this Q tilde in this limit when Q goes to 1, first when omega 1 goes to 0, but omega 2 is fixed, then this goes to 1, but this blows up and exponentially fast goes to 0. Therefore, this factor exponentially fast goes to 1, and this is very easy to estimate. And already from this from the asymptotic value of this gamma q, you can derive this limit. And Simon did it in a different way. Using some shifts for the parameters entering this hyperbolic hypergeometric function, applying this inversion relation and taking the limit omega to 1 from this integral, you go down again back to this integral, Mellin-Barnes plane hypergeometric integral. So you close up. Two different ways of degeneration give you exactly the same function. Okay, of course, all I am saying can be generalized to the multivariable cases, to the root systems, and so it's just technical thing. But all the important principal things emerge already at the univariate case. Now I'm talking about the complex hypergeometric functions. That's what was rarely mentioned in the literature on integrable systems. So here's the exact formula for Euler's beta integral, very well known to everyone of you. What's the complex analog of this? So I take two parameters, alpha alpha prime, general complex, whose difference must be integer. That's very important, because only under this constraint, the functions defined by these integrals will be univalued. Now I use the definition of this for the notation, when z in the square brackets in the power alpha is actually z in the power alpha and complex conjugate of z in the power alpha prime. And it's univalued because of this representation. That's exactly why you need this integer value of this n alpha. Here's the measure which I define on the plane in complex notation or real notation. And Gelfand, Graev, Vilenkin in their book on generalized functions have defined the following analog of this Euler's beta integral of the following form. So omega minus z1 in the power similar to this one. This is a factor similar to this one. Instead of the unit cut, you have here full complex plane, and the integral is computable exactly, and it's ratio of these 6 gamma functions. But look, gamma alpha, gamma beta, and gamma alpha plus beta. It's exactly the repetition of this guy. And the others also repeat itself. Gamma alpha divided by this, gamma beta by this, and gamma this. So that you can actually combine these pieces into one function. Here it is. And this is the complex gamma function. So it's the gamma function over the field of complex numbers. And I use double notation in the literature. There are both notations, this and this. So what's the difference? This is in terms of alpha alpha prime. But if you parameterize alpha and alpha prime explicitly, here is the half integer with the opposite sign. And here you put I, x. And so the difference is just n, evident. Why I write X complex and simultaneously single out this I? The reason is the following. This function will appear in the representation theory of the SL2C. And when X is real, then the objects, those objects will be describing the unitary principal series representations of this SL2C algebra. That's the reason why this parameterization is important. And I will be talking about SL2 6J symbols for SL2C algebra or group. And in that context, reality of the 6 will be exactly corresponding to the 6J symbols for unitary principal series representations. Okay, from these standard relations for the Euler gamma function, one can deduce a number of useful relations for this complex gamma function. So permutation symmetry, this one or this is the same, just different notation. Or this is the exactly inversion relation in this form or in this form. You just invert the sign of the continuous parameter x and shift it slightly, and that's it. It works already. And here are the functional equations for this complex gamma function. Of course, they are derived easily from the functional equation for the Euler gamma function. And using this complex gamma function, now this beta integral, complex beta integral takes the following form. You can write it in this form. Now you exactly see that it repeats the form of the Euler's beta integral. But using the inversion formula, you can even simplify that and write in the following form, the product of three complex gamma functions in the numerator with the constraint on the parameters entering these as arguments into these gamma functions. And here's the notation I use, the product of gamma functions. So that's the standard form of the complex beta integral, but applying the SL2C transformation, which is a rational projective transformation for each variable, inversion and some shifts of external variables omega z1, z2, you can rewrite this previous integral in the following form. So we have three now three ingredients of this integral. Alpha, beta, gamma again should satisfy this relation, and then it takes the following very nice form. And this form is called the star triangle relation, and it was used very widely in the computation of Feynman diagrams, and it appeared also in applications to non-compact spin chain. So this formula is very useful in various fields. I will not mention that. Just historically, complex hypergeometric functions emerge in two-dimensional conformal field theory in the work of Zenkevich intensely discussed. In particular, the Zelberg integral was discussed there. Separately, it was considered by Aomota. But the whole consideration of these complex hypergeometric functions emerged first in the work of Naimark, 1959. He was building the 3J symbols for SL2C group, and so the elementary functions, but the scalar products involved in the orthogonality relations, they are exactly given by complex hypergeometric integrals. So in a sense, in particular, the conformal triangle emerged first here as this 3J symbol in this representation theory. And relatively recently, the 6J symbols for this group were constructed by Ismagilov. And we, 10 years later, with Derkachov, derived his result with some small correction. And so also in a similar way as in Naimark's work, these complex hypergeometric integrals emerge in this setting, but in a different form, not in this form, in the form of Mellin-Barnes representation, which I will describe now. So remember this. Form of the complex hypergeometric integrals, then they will appear a completely different form, which actually looks rather awkward. And I will derive that as a limit, a special limit from hyperbolic integrals, hyperbolic hypergeometric integrals. Formally, these limits were appearing first in the work by Zhanes, Mangaziev, and Sergeyev, and in now almost 2 years ago, jointly with Sarkisian, we made these limits, all these considerations rigorous, and it goes as follows. So you take this gamma, small gamma without indices, which is the ratio of two infinite products, and choose a special parameterization for the argument u and this quasi-periods omega-2, omega-1, the following one. So square root of omega-1 divided omega-2 is denoted as b in the conformal field theory in two-dimensional. And the limit when b goes to I, so delta goes to 0, it corresponds to b squared to -1, or central charge goes to 1. So this is C equal 1 conformal field theory, essentially. So easy to substitute and see that omega 1 plus omega 2 vanishes in this limit in the following way. Inverse is this form. Now the things appearing in the exponents have very simple limiting forms. Now, what to do with this argument u? This argument should be chosen in a very peculiar way. You have to scale out by this variable, which emerges here in the integrals. You saw it already in the measure. So it should be scaled out. And then the leading piece of the argument must be integer. That's the trick. And this is the continuous argument emerges only in the vanishing piece of this argument. And the leading piece here is integer. Then when delta goes to 0, q goes to 1, of course, because you have here -1 gives you unit, and then you have unity. And then this infinite product, now explicit parameterization here. The trick is the following. This integer, when you substitute here, disappears in the leading piece. That's exactly the trick which works in this case. Why this limit is so peculiar? Because the argument now has a qualitatively different form, and you can rewrite this infinite product as the ratio of this expression, explicit expression, divided by this Jackson's Q gamma function. You see the arguments are here, also have vanishing pieces. Similarly, when q tilde, this model transformed, omega 1 divided omega 2 goes to -1, and omega 2 divided by omega 1 goes to -1. So this goes also to 1, not to 0 as in the previous case, but to 1. Both q and q tilde go to 1. So this second infinite product also starts to blow up. And it has the following representation, again, the explicitly known piece of a function. And now Jackson's Q gamma function is Q replaced by Q tilde. So this gamma function is the ratio of two Jackson's gamma functions. Then goes the ratio of two infinite products, modular transform divided by initial one, and this elementary function. Now, this piece, this ratio, can be computed through the modular transform for the dedicated function, which I have shown you. So here is the exact expression, and in the limit delta 2 goes 1, it's just a root of unity, exponential pi I divided by 12. So very cute phase factor emerges from here. And finally, when you apply this q goes to 1, q tilde goes to 1 limit to this ratio, of course, you get the ratio of gamma functions. And the combination will be precisely the complex gamma function. And this will be the elementary function. Here is the explicit asymptotic formula. So arguments and omega 1, omega 2 parameterized in the following, and delta goes to 0, is blowing up at the following speed: 4 pi delta in the power ix minus 1. Some root of unity emerges. And depending on, and is exactly this complex gamma function. And that's it. Now you apply this. This is uniform limit according to Rein's and Carvin the results about the uniformity of limit for Jackson's Q gamma function. And you can apply now this limit to the hyperbolic integrals. And it goes as follows. So infinite contour, this is imaginary axis of some particular meromorphic function. This is the measure which you saw already. So first you rotate it to make the contour of integration real, by just scaling them up in this way. Then you split this infinite interval into the infinite sum of unit cut intervals defined in the following way. Then you shift arguments of this integration so that you take out these n's from here into the argument of this kernel. Then you change a variable x by y delta, where delta will be vanishing. And so now you have the following expression. And since I passed to the integration by y, my interval integrations become 1 divided by 2 delta and minus 1 divided by 2 delta. So for delta goes to 1, they go to infinity. And essentially, this integral will be described by asymptotics of the kernel, which is hidden here. Rather tricky thing, and it works in the cases when this limit for this kernel is well defined, which is exactly the case for this hyperbolic hyperbolic integrals due to the limit that I described for hyperbolic gamma function. So now I apply this limit to the hyperbolic beta integral, which emerges if I take this G8 parameter equal to omega 1 plus omega 2 minus G7. Then G7 disappears completely because of the inversion formula for this gamma function, gamma 2. And here is the exact answer for this computation. This is the limit of the elliptic beta integral. Right-hand side is known explicitly. So what I do the following. I parameterize Z in the following way. So again, leading term is in some integer. And this is the continuous term. Parameters GK in the same way, some integers and 6 integers. And again, continuous piece is vanishing. Note the trick. These now N and K are not integers, but either integers or half integers, which is very important because it's a freedom which is emerges in this way. And the balancing condition, which I used before for definition of the hyperbolic or elliptic hypergeometric integrals, now splits into two pieces. The sum of integers must vanish, and the sum of continuous pieces alpha k must be minus 2i. And so piece by piece, we rewrite this into exactly computable integral. And so in the kernel, we have 12 these hyperbolic gamma functions, which now take the asymptotic form of this type. And you see it blows up 1 over delta in the power 8. The same blow up takes place in the right-hand side, 1 over delta in the power 5. And everything is like a complex gamma functions. Then in the kernel, we have also this piece, which is explicitly written in this form with these ordinary gamma functions. The ratio is complex gamma function, and it's computed as 1 over delta squared, very nice factor. So when I substitute all this into this relation, then this common divergent factor on both sides cancels out, and here's the exact relation which you get in this way. So sum over these integers or half integers of this measure, which emerges on here, times 12 complex gamma functions. Here is the notation which I use. Now plus minus should be taken simultaneously for the continuous and for the discrete part. And the right-hand side now is the triangle product of these complex gamma functions. So special cases of this relation non-rigorously were considered in that paper by Bazhanov, Mangazeev, and Sergeev. But here we have the most general relation defined in this way, and it is established rigorously by a completely different method, by direct computation, essentially. This formula was also a little bit later was proved by Derkachov and Monashov. And they just computed as it is. We derived it as a limit from hyperbolic integrals. Okay, as I mentioned, this V function, elliptic hypergeometric function, it satisfies it has the W7 group of transformations described in the Zyberg duality, simple Zyberg duality. And I would like to raise the physical question here. So it's at the 4-dimensional field theory level, it's Zyberg duality for field theory is defined on this topological manifold, S3 cross S1. Shlomo mentioned it. If you go to hyperbolic integrals, you go down from 4 dimensions to 3 dimensions, and those hyperbolic integrals describe partition functions, supersymmetric partition functions of 3D supersymmetric field theories defined on the squashed S3. Now I take this complex limit and go to 2-dimensional field theories. If I take trigonometric limit from trigonometric to standard plane hypergeometric, then I get what is called the vortex partition functions. That's we considered some time ago with Vartanov. But here I have complex analogs of that, and here is the explicit form of this relation. So, and this W7 generating transformation for this W7 group at the level of complex hypergeometric functions. You see now I have not 6 as before, but 8 parameters alpha k. And the balancing condition of this form and this form. And so this is the symmetry generating this transformation generating this group. And the physical question is, we don't have yet a completely clear picture of what it describes at the 2-dimensional level, say at the level of vortex functions. It, of course, describes something for C equal 1 CFT, because this integer is essentially, it's a spin variable of this conformal group which emerges there, but also it is not yet completely well understood. Some work is in progress, and more understanding is necessary for understanding the picture at this two-dimensional level. Now, by taking now the parameters gk, some of the parameters to the infinity, we can simplify that relation to the following one. Here is the we have only 6 parameters, simpler form of the kernel, which are involved in the hyperbolic beta integral. Again, a substitution of this limit yields this type of relation. And if you take this parameter nu, integer value, so nu is equal to 0, it corresponds to integer values of all discrete parameters. Then it has been shown by Derkachov, Manashov, and Valenevich. Then this will be exactly the Mellin-Barnes representation of that complex beta integral, which was essentially discovered by Gelfand, Greif, and Vilenkin. So this formula, just for your kind of educational reference, is equivalent to this formula. You just need to pass from this two-dimensional complex integration to the Mellin-Barnes form to make some integral transformation. Then this formula will be passing to this formula which I derived as a limit from the general situation. So it's so essentially this is also, you can go back and so describe this relation map to the previous two-dimensional integral formula. Now about the 6J symbols. So as I mentioned, Ismagilov derived it first, and we have noticed some kind of small, not mistake, but so one of the signs in the Ismagilov's answer should be changed in our result. And we think we are right. And a third independent consideration is necessary to decide who is correct, we or Ismagilov's answer. We believe that ours because we have different checks. So here's the answer for this 6J symbol. You know, 6J symbols emerge as the interbase integral transform. In this case, it will be not matrix, not finite dimensional matrix, but the integral operator, which maps. You take triple tensor product of principal series representations, and so through the 3J symbols construct 2 different expansions of this triple product, and the integral transform which connects these 2 representations contains as a kernel exactly this 6J symbol. And here is the answer which we have obtained. So it is given by 3-dimensional complex integral or 6-dimensional real integration. So one variable complex is here, another is here, and third is here. And you see these ingredients are just integrals, complex integrals of elementary functions, looking similar to the previous integrals that I have shown. So this is one representation of these 6J symbols. In order to pass to Mellin-Barnes representation, one should use some particular formula for this, say, for this factor, which allows you to separate variables z and y. It's some kind of integral transform involving sums of integrals, and that's, you just replace it here, and then suddenly all the 3 complex integrals can be taken explicitly due to the star triangle relation, and you get the integral which I will describe next. So first I use this parameterization. This A parameters LC, C prime, these are parameters of the representations, these triple representations, unitary principal series representations. So you parameterize it as half integer and some imaginary integer. When sigmas are real, then this is exactly unitary series, in principal series. So don't pay much attention to the parameterization. I just show you that if you substitute here such a parameterization and map through this integral transform for this propagator, which I described, the separation of variables, and now redenote it, the same object as the standard notation for the 6J symbols, then you can rewrite it as the following expression. So with the product of complex gamma functions, 1, 2, 3, 4, some signs of pi, then exactly that's what emerges in the Mellin-Barnes form. Sum over lattice of integers and integration over infinite condor from minus infinity to infinity of the product of 8 complex gamma functions. And here's the exact relation between these continuous parameters Ru and sigmas and integers sk, tk in terms of integers which emerged previously. And these a's which emerge here, they are given here. And you have the kind of balancing constraint which requires such limits for such constraints for the continuous piece and the discrete piece. That's essentially what we derived with Derkachov, rewritten in terms of complex gamma functions. In our paper, it's written in a different form. We just written in equivalent form. Now about the equation for this. Probably this is the best new result which I describe in this talk, because this is not published yet. It's in preparation in a joint work by Derkachov, Sarkisyan, and myself. Let's start from elliptic hypergeometric equation, which I derived in my adaptation thesis. It has the following form. So it's second order Q difference equation. Here is Q, x, Q minus x. Ax is a ratio of 8 theta functions divided by 2 theta functions. This is evident, inversion. And lambda is the product of six theta functions. This is the balancing condition. And there is nice, cute constraint on the values of this epsilon 7 and epsilon 8 are related through the multiplication by Q. Clearly, this is a special case of the Van Dien n=1 Hamiltonian. Well, it has the structure of that type. In order to see that it can be obtained from that, one has to impose particular limits, particular choice of values of the parameters of the Van Dien model. And the solution of this form of elliptic hypergeometric equation is given in the following way. So it's essentially V function with very strange parameterization of parameters. Where it involves some roots and divided by some elliptic gamma functions. You can rewrite this equation in an opposite way, when the solution will be given by V function with completely symmetric form of these parameters. But then the coefficients involved will be looking awkwardly complicated. So it's two forms of representation. I just taken this in order to show that it goes to these n-body integrable systems. Now, if I skip a lot of steps and go down to this complex hypergeometric level, namely to the level of 6J symbols, which I just have described, then this equation degenerates to the following form. So some potential B times U, where U is the sum over Z integrals. So it's essentially the previous the 6J symbol up to some simple prefactor, which is combination of gamma functions. This is different prefactor, but this is a key point. And so the coefficients emerging here are just rational functions. You see explicit form. These are now complex variables and integers involved. What is important is the following one. Now you have not just difference equation, but actually the mixture of recurrence and difference equations. You see, you shift not only continuous parameter. When I write this, as I assume the following, that this function is given here. Actually, it's U function given here with S2 and 2 shifted by minus I and minus 1, but S3 shifted by plus I and plus 1. This is needed in order to preserve the balancing condition, because as soon as you shift this, then you must shift additional parameters in the backward direction. And I choose here S3 as this backward direction shift. So this here involves actually 2, but because of the balancing condition, it actually difference equation shift only in one variable. And also you have to shift the integer value by 1. So it's not plain difference equation. It's, if you wish, two-dimensional finite difference and discrete recurrence relation. And this is a new type of equation. And of course, it goes down to generalization of, say, rational limit of Ruijsenaars-Schneider problem. If you take hyperbolic Ruijsenaars-Schneider problem and consider eigenvalue problem, then in this limit, which I just described, you will get not the finite difference equation, but this type of recurrence difference equation. And this is a new thing, which, as far as I know, never was discussed in this integrable systems business. And it is necessary to understand what's going on with such type of functions. And in particular, as I said, physical interpretation is needed. And this, well, one interpretation is already known in 2 dimensions. These are conformal spins. So one has to dig deeper in this type of interpretation. And that's the work also for the future. Okay, do I have more time, Peter?
Yeah, sure. You can take several minutes.
Okay, then I can describe another new thing. And it goes to similar but different limit from hyperbolic integrals, hypergeometric functions, to the rational level. Again, new degeneration and new things. Just to remind you, what was the limiting formula for the hyperbolic gamma function, which gave all these surprises in this way? It was this one. Here it is. So this is Faddeus modular dilogarithm or hyperbolic gamma function with skewed parameterization. Gives you complex gamma function, ratio of two gamma functions. Note that here I have I. So I take the direction along imaginary axis of the argument, and Q goes to 1. Well, the argument. Well, so just remember this I. You take the one particular direction for this integer, leading integer values for the argument. Now I took different along the real axis, if you wish. Here it is. So first, I take B, this CFT to the CFT parameter, as goes to 1. And this corresponds to CFT charge, central charge equal to 25. It's well-known also limit for the central charge. And the parameterization now goes as follows. You see here I have now real n leading integer value instead of I. So different direction of the argument of this gamma function. And y also continuous parameter. And the point is that the crucial thing is that this, if you take this limit and generic value of argument, nothing happens. Nothing. It's very simple. This function is well defined unless you choose this particular form of the argument. Only then there appear the divergences. So here is the limit. When delta goes to 1, this guy either blows up for positive, for negative n, or goes to 0 for positive n. N is integer. And now instead of ratio of full gamma functions going to complex gamma function, you have the ratio of the sign of arguments change, and you have now this Polynomial symbol of the following form. Here is the Polynomial symbol. It's just the polynomial in for positive n, or 1 over polynomial for negative n. So this ratio of gamma functions, which was in the previous things, here it becomes just the Polynomial symbol. And now apply this limit to this, say, hyperbolic beta integral, which I described. You get the following. So balancing condition again splits into two conditions. Now sum of integers must be equal to 2, and sum of continuous variables must vanish. And here's the answer. 1 over 8 pi I, sum of either integers or half integers. This again, of course, appears similar to the previous case for in a similar way, looking similar, just the sign changes. And here you have 12 Polynomial symbols. So this is rational function of arguments. Integration goes over the real axis essentially. If this control should separate the poles which emerge for plus sign and minus sign Polynomial symbols. So they must lie on two sides of this control integration. And here's exact answer. Again, you have triangular product of this Polynomial symbols. Exact new formula completely in this limit. We call it rational hypergeometric identities, this type of relations. The trick is the following. This sum is finite. I wrote it as an infinite sum, but in fact it is finite. The point is that when n is sufficiently large, all the poles of this kernel lie on one side of the integration contour, and evidently by complex analysis, this integral vanishes, so the sum terminates both from above and from below. So actually you have here the finite sum of integrals of this form. By residue calculus, you can compute these integrals explicitly. It will be given by some rational function. So essentially what you have on the left is the finite sum of rational functions of the arguments involved into this computation. And it is collapsing to the very nice product of Polynomial symbols. So this is summation formula of a new type. And again, taking this limit of this elliptic hypergeometric equation, going to down to hyperbolic level, then going to rational level, this should give something also new for the rational level, but we did not consider yet this limit. It's also it should be considered, and I hope that it will give also something new about another degeneration of hyperbolic Ruijsenaars type of models. So thank you very much for your attention, and please, if you have questions, go on.
Thank you very much, Slava. Please, questions?
So, Slava, can you go back to the slide where you had the physics question?
Okay.
I don't remember.
Yes, you're exactly the right person to pose it. Just a second. Here it is. Limit. Oh, here it is. Yes.
So this, the structure of these sums and integrals is exactly the structure of what is called S2 partition functions in 2D. So it looks like an identity of S2 partition functions of some supersymmetric.
Yes, you mean the two field theories onto these ones reduce for S2.
Right. So the way you do it, you start from the index in 3 dimensions, and S2 times S1, and reduce, and then you get these types of identities: infinite sums and integrals.
Yeah, but I stopped looking for that piece of literature for some time ago because essentially Vartana departed and I went to different problems considering more mathematical. So that's a two-dimensional thing. But what's the meaning of these integers in that picture?
Oh, it's flux on S2.
Fluxes. Okay. I should probably ask you about the references about these things.
So it looks like that, but it's actually a very rich story there, which is poorly understood physically, because it so happens that when you go start from Seiberg duality, like your top integrals, and then you go to 3 dimensions, so dualities in 4 dimensions basically reduce to dualities in 3 dimensions. But if you do the same thing going from 3 to 2, you get some identities, mathematical identities of this sort, but sometimes they imply dualities and sometimes they do not, because sometimes if you compute other things that should be equal under dualities, they are not equal. So it's actually a much richer and more complicated story.
Shlomo, thank you. I should ask you about that literature and look for it better, because we postponed for physical consideration things, and I think there are new phenomena and new things which I understand, but I think it was not considered in the literature completely. But that requires better consideration. I will talk to you later.
Thank you.
Other questions? Okay, great. So I think let's thank Slava again. It was a nice talk. So Slava, please email me your slides. I'll put them on the website.
Just a second. I will.
It's not urgent. You can do it like after.
Yes. I should.
Okay, so I guess that's it for it's the last talk of the workshop. So thank you very much for joining. So we'll have. I hope it was fun for you guys, for everybody to listen and to participate.
Thank you for organizing it.
Sure, yeah. So
Thank you, Peter.
Yes,
I hope next time.
Thanks a lot, Peter.
Absolutely.
Thanks a lot.
Sure. Yes, I guess we can continue the discussion over the email, because I think, at least myself, I have a list of questions to ask to almost every speaker. So, yeah, so I wish we had a little bit more time for discussions, but yeah, I think it's fine anyway. Okay, so yeah, so maybe next time we'll meet together in a live, in some actual venue, not over Zoom. Yeah. Okay, great. Thank you very much, guys. Bye.
Thank you.
You have very nice weather. We have here -20.
Yeah, I thought he was flaunting it.
That's a palm on my backyard. Yeah.
Very jealous in a sense. Okay, see you.
Bye.